I decided not to try to make any remarks, serious remarks about Maxime, because I already said at the dinner, my memory is terrible, so what I say is usually wrong anyway, and what I want to say is too much and would be inappropriate. But because of this brief introduction, let me say very briefly, I sometimes hear somebody refer to me as the teacher of Maxime. This would be a wonderful distinction. That would make me one of the important mathematicians of our time. It's not true at all. When Maxime came to Bonn, we had already met. He came twice, and actually he had met me in Moscow. I'd given lectures, and he had seen me, but I didn't know him yet. And he wanted to do research, and the director of the institute, my friend and supervisor, Hirzbruch, said, yes, but we can only pay you 700 marks a month if you're a student. You need to have a PhD, and he did not have a PhD, not even Kandidat. He had no PhD. And Hirzbruch said, I've no room to take a student, but maybe you work with Don Zagier. So very, very shortly afterwards, there was the famous Arbeitstagung. Attia gave, as always, until he stopped and Maxime took over. But for 35 years, the opening lecture was always by Attia, always very brilliant and always on the index theorem and some of its applications. But the content changed every year. And he explained Witten's conjecture. And at the end, I was in the front row as usual. I'm nearsighted, Maxime in the back because he has good eyes, or had good eyes, maybe still. So I brought him to Attia and I said, let me introduce you to my young student, Maxime Konciewicz. He's the person who will prove the conjecture you just told us. And Attia looked at me like, I always knew you were a little crazy, but this is ridiculous. So he looked, yeah, sure. This, as always, the opening is always on Friday. On Monday, because the lecture rooms are busy, the professor using, we always had the boat trip, which is 3 hours one way and 2 hours back. And the entire 5 hours, Maxime and Attia sat together, and Maxime explained his proof, which he had found in 3 days. And Attia since then had much more respect for me. So I was not in any sense Maxime's teacher. The only thing I did is to introduce him to Attia and say the famous words, this is the young man who can prove the conjecture. I had no idea how, and frankly, after he did it, I still had no idea how. So I should perhaps also say he did have teachers, several, all of whom I knew. 2 are no longer with us. One was Israel Gelfand, one was Yori Manin, and the third was Sasha, who sits there. So if you ever use the word Maxime's teacher, please think of Sasha, not of me. So he's not that much older, but when they were still tiny little children in Moscow, he was a little older and he taught his younger mathematics brother mathematics. So when Maxime came to Bonn, he knew much, much more mathematics than I will certainly ever know. So, okay, that was a short personal remark. Now the lecture starts, and if somebody's timing it, it only starts now. Okay. So the title of my lecture is Modular Forms and Differential Equations. And I should say right at the beginning, my goal was very ambitious. I wanted to present a beautiful solution to a beautiful problem. The problem is due to Maxime. The solution, unfortunately, doesn't exist yet. It's not that we don't yet have the proof, we don't yet have the statement. The we, I'll say later, is a colleague in China. We're, I think, very close. So this has to do with, well, with mirror symmetry and so on. I'll come to it later. So I will talk about that a little at the end, but I will not be able to tell you the culminating, exciting result that I hoped I might have. So I want to start with the general result. Think of the special functions of mathematics. So there are many that we know the names. So for instance, you have Bessel functions, hypergeometric functions, Legendre functions, and for instance, the gamma function. Now the first three, ask any mathematician, what are Bessel functions? Well, he'll say they're the solutions of Bessel's differential equation. And basically the same is true for hypergeometric. Of course, there's a series. And the same is true for Legendre and Hermite and many other special functions. Of course, the gamma function does not satisfy differential equation, but most of the special functions do. But the point I'm making is that when they do, that's the essence of the theory. Any book on Bessel functions starts with the differential equations. Now we come to another important class of functions, my favorite, which is modular functions and modular forms. They also satisfy differential equations. In fact, several different kinds. That's the theme of my lecture. For some reason that I've never quite understood, this never became the center of the theory. And in fact, many specialists, even today, in modular forms don't even know the fact that I said, actually it's 4 facts, 4 kinds of differential equations. It's completely ignored. We do Hecke operators, which are of course the most important, and Rankin-Cohen brackets, all kinds of things, but not differential equations. So this is a little sad, and so I want to make a little propaganda for this point of view. So what I want to tell you is that modular forms, so I will always abbreviate because I'm lazy and the word will come often. MF is not male and female, or something about wild animals. It's modular forms satisfy differential equations. But actually, as already said, it's several different kinds. I've known about 2 for many years, 3 a little less, and 4 only quite recently. So during the talk, I'll talk about all 4, but I won't write them yet. As I go along, I will and try to remember to add it to this overview. So maybe since I've enough boards, if I throw this up a little, oh, it doesn't go out of, even I can reach this. Okay, so first I remind you very briefly what modular forms are. So you have some group gamma in SL2R, a discrete, and let's say cofinite volume. So the basic example is, e.g., gamma might be the group I'll just call gamma 1, so I don't have to keep writing it, SL2Z, or maybe a subgroup of finite index, but there are many, many other groups, including groups that have compact quotients, so like the groups associated to Shimura curves. And then K for us will be the weight, will be a positive integer for what I'm saying now. So a modular form, and I'll use Z, but I'm used to tau, so if I forget and write tau, it means Z. F of Z is a modular form of weight K. So that's denoted by mk of gamma. And this means, of course, you've all seen this formula, but just for completeness, I remind you that this means that for all Z in the upper half plane, so this is a holomorphic function in the upper half plane with some growth condition that I won't bother about, and gamma is an element of this discrete subgroup of SL2R. You have this equation, and then the basic facts are m star of gamma, which is the direct sum. So if k is negative, there are none. If k is 0, it's just the constant. So this is a graded ring with unit, and this is a finitely generated graded ring. It may have many generators and many relations, but the transcendence degree is always 2. So the simplest example, and then I'll also give examples of modular forms. If I take gamma 1, again, all of you know this, it's to remind you to relax and also to fix notation. So I give you the simplest examples. E4 of Z is 1 plus 240 times the sum n cubed q to the n over 1 minus q to the n. Q, now and for kind of universally in the theory, means e to the 2 pi I z. Z is in the upper half plane. So Z is in the complex upper half plane, and Q is therefore in the open unit disk. So E4 is this, and that's a modular form of weight 4 on gamma 1. And similarly, E6 is exactly the same formula, but the coefficient is now minus 504, and the exponent of n is n to the 5th. And there are similar Eisenstein series E8, E10, and so on, and they're given by the same formula, n to the k minus 1, some constant, and because of this theorem, they're all polynomials in E4 and E6. So this is just a very quick reminder
So do we require functions to be bounded at infinity?
I said that. I said they're holomorphic functions with some uninteresting condition in infinity that I don't want to repeat. Everybody who could care has seen it, and everybody who doesn't care, and how right they are. Okay, so that's just to remind you. So now I want to say that there are 4 kinds of modular forms. And so the first kind is linear. So DE means differential equation. L, this is pretty universal, is linear differential. That's good. Linear equations are good. Nonlinear are bad in the sense they're very hard to solve. But of course, they're much deeper and much more interesting. So it satisfies a nonlinear expression. So f of z is a modular form. Then f of z satisfies a differential equation, which is linear. Its order, the order of the differential equation is exactly k plus 1. So the weight of a modular form can be even negative if you allow poles or half integral, but then this theorem isn't true. So here you need k to be an integer, but not with respect to z. So that's bad. So f is a function of z. A differential equation should involve f prime of z, etc. By the way, let me write, when I write f prime of z, I actually will always mean 1 over 2 pi I. So the prime is with respect to 2 pi I. That's because of this q. If you have a sum a n q to the n, then its derivative will then be simply na n q to the n, and you don't need all these stupid 2 pi i's. So, but it will not be a differential equation of that. Instead, I'll have f is a modular form of weight k as before, and t is what's called a modular function. Again, almost everyone knows, but I'm just reminding you of terminology. Modular function means it's a modular form of weight 0, so it's simply invariant. Gamma z is, of course, az plus b over cz plus d, and such a thing must have poles somewhere, for instance, at infinity. You can't have it bounded everywhere. So you pick any. And the theorem is, if you have any modular form of positive integral weight, it doesn't even have to be holomorphic, it could be meromorphic, and any modular function. And if I write f of z as a function of t of z, well, you'll say you can't, because I replace z by gamma z, then t of z doesn't change, but f of z does change. So indeed, you cannot have this everywhere, but you can have it locally. And then as you move around, you'll get monodromy, which is rather good if you want a differential equation. Okay, then phi satisfies, so as a function of a new variable, phi of t, satisfies an LDE, a linear differential equation of order, as already said, k plus 1. So this is a basic theorem. It's been known certainly for more than 100 years. But as already said, strange enough, even some specialists don't know it or aren't that aware. So I'll give 3 examples. So the first one is, when I gave my examples of modular forms, I forgot a rather important one. So I forgot 8 of z, which is q to the 1/24th times the product 1 minus q to the n. That has weight half, which I didn't allow, but whenever I have an 8 in this talk, anyway, believe me, it'll be okay. Everything will have integral weight. So 8 is this, and then there's a famous identity. So 8 to the 12th, 8 to the 24th, which is called delta of z, is e4 cubed minus e6 squared over 1728. So I'll use delta all the time, so I wanted that still on the list. So my first example, f of z, is the simplest theta series you can write down. It's the sum n in z, q to the n squared. So that's a modular form of weight 1/2. I don't want weight 1/2, so I'll square it. And t of z is the Legendre function up to doubling t, so it's 16. This I can never quite remember the exponents. 8, 4z to the 16. The formulas don't matter, I'm just writing them so you see that there are formulas. So this is a modular function of the group gamma of 2, of index 6 in SL2Z, actually in a slightly smaller, bigger group. And now, f of z, goes back to, I guess, Legendre probably. It is f, when I write f, I always mean f21 of 1/2, 1/2, 1, and t of z. So here, the weight is 1, so the order of the differential equation is 2, and the most familiar second order differential equation maybe is hypergeometric. Example 2 is very similar, so I'll write it even more quickly. F of z is E4 of z, which I already defined. T of z is 1728 divided by the modular invariant, which everyone has seen, but I'll still remind you. It's E4 cubed over delta, which is 8 to the 24th. So it's this, and then this is a form of Fricke and Klein, so around 1900. F of z is again a hypergeometric function. Now with this. So those are two simple examples. But I want to give a more interesting example. So example 3. Apéry, now I can't remember the year, it was maybe around 1983, 84. I don't remember the year anymore. Proved that zeta of 3, the famous number zeta of 3, is irrational. And he proved it in the following way. Again, now I have to check so I get the numbers right. Actually, I do remember them by heart, but I want to make sure. Maybe I won't look, and then you'll see that I actually do remember these numbers. So you have a sequence of numbers an, and they're defined by recursion. N plus 1 cubed times an plus 1 is 34n cubed plus 51n squared plus 27n. Again, the coefficients don't really matter, but just to be precise, I'm writing it all down. So here's the recursion of the ans, and now you see something extremely remarkable, which is that assuming that an and an minus 1 have already been found and are integers, this is an integer, but here I have to divide by n plus 1 cubed. So a priori, an has a denominator n factorial cubed. Then the first Apéry miracle, so he gave an explicit formula which made it clear why the next property is true, but it wasn't at all clear why those numbers satisfying his formula, they were integers, why they satisfied this recursion. But we have this. But now I also define a new sequence which starts 0, 6, 351 over 4, and so on, by the same recursion, the different things. Then again, so a priori, n factorial cubed times an or bn is in z, trivially. But an has no denominator at all. And so the second fact, so this is the first fact that Apéry proved. The second fact is that bn has a much smaller denominator, relatively small denominator. So it's not n factorial cubed, which is like n to the 3n. This is less than 20 to the n. So it's still exponential, but only exponential. And the third that Apéry also proved is that bn over an tends rapidly to zeta of 3. So just to make that come to life, I actually wrote down the numbers. So for instance, b4 over a4 starts 1.202096903157.8, and zeta of 3 starts this can't be a, oh, it's a 4. I know it's 205, but I couldn't read it. 202, my handwriting is terrible. So you see up to here, they agree. So it's an extremely rapid convergence. And from this, it's trivial to deduce that zeta of 3 is irrational. It takes 2 minutes, but you have to discover these 3 facts that Apéry discovered. And what was found then by Burgertz, only 2 years, I think, or 1 year after Apéry's proof, is that if I choose t of z to be with the same 8 as before, 8 of z, 8 of 6z, over 8 of 2z, 8 of 3z, to the 12th. And f of z, so this is a modular function because a half plus a half minus a half plus a half is 0. F of z is 8 of 2z, 8 of 3z, quantity to the 7th, divided by 8 of z, 8 of 6z, quantity to the 5th. So this is weight 1. So this thing starts q minus 12q squared plus 13q cubed, and so on. And you just expand it and you find. But now comes the point. It's obvious that these coefficients are integers because eta is given by a product, and so everything is integral. But now this satisfies the differential equation by the principle. A differential equation is equivalent to a recursion, and so you now prove in one line that this, if you expand f as a power series in T, then the coefficients are exactly the Apéry numbers. And therefore, since these both have integral expansion, that gives a one-line proof of the integrality, which was very mysterious before. So that's my first example, is that modular forms satisfy linear differential equations, which is very good, order k plus 1, but not with respect to z, it's with respect to t. But now the second.
And is there a similar proof for Bn being a small denominator?
Sorry?
Is there a similar proof that Bn has small denominator?
Yes, that's a good question. So of course there's a modular proof for both parts. So if you make the generating function some Bn, t of z to the n with the same n, it has denominators, but its q expansion, the nth term has denominator only 1 over n cubed. And the reason is when you take that function, it's what's called an Eichler integral. If you differentiate it 3 times, you get a true modular form, some Eisenstein series. So with integer coefficients. So the nth coefficient of that has denominator exactly 1 over n cubed in q. Now when you change from q to t, the nth coefficient is some combination of 1 over 1 cubed, 1 over 2 cubed, up to 1 over n cubed. So it's the least common multiple of the numbers up to n cubed, and that by the prime number theorem is e cubed to the n, which is a little less than 20 to the n. So thank you for the question. So indeed there's, and then also for the same reason, you can prove from that formula very easily that the limit is 8 of 3. So the whole thing becomes very clear in the modular world. So now the second kind is nonlinear differential equation. Well, so I'll start with good and then bad because I'm an optimistic fellow. Now it's with respect to z. Remember, this with respect to t of z. We have to change variables to a modular function. And then phi satisfied the differential equation, but with polynomial coefficients in general algebraic, but I'm lying a little. So this one is with respect to z itself. That's good. Maybe I'll put exclamation marks to show how excited I am. But
you're right.
Sorry, good is not bad. You see, I'm so excited that I can't tell good from bad. It's a kind of a moral blackout. Okay, so it's with respect to z, it's order 3, which is really good. This doesn't mean 6, which is 3 factorial. So the order doesn't even go up, and it's even autonomous. Not everyone remembers the word from university. Autonomous means a differential equation which doesn't contain z, the independent variable at all. It's just relation among derivatives. But it's a nonlinear differential equation, and this, as I already said, is bad. Okay?
Still algebraic, which is good.
Well, yeah, well, of course it's good. Everything is good, but even this is good, but you have to be feeling very friendly to think of nonlinear differential equations as good. So let me give you the proof of that. So here I already had m star of gamma for any group gamma, and I explained what it is and that it's finally generated. But there's a bigger group called m star. So this is modular forms, and this is quasi-modular forms. This was a word, certainly there were examples going back to Eisenstein, but this is a word that was introduced by Masanova Kaneko, who's sitting there, and myself, in a paper many years ago, and we gave a formal definition and many properties. So this is quasi-modular forms. And our definition was a bit different, but Werner Nahm found a very beautiful definition. His definition, f is again a holomorphic function in the upper half plane with some growth condition. So the previous definition, if I put the cz plus d on the left, this was just f of z. And now the definition that Werner found looks completely crazy when you first see it. So gamma is, a, b, c, d. It's simply that you have some polynomial, any polynomial of C over CZ plus D. So it looks completely crazy. But let me show you that it's not completely crazy. So
F of Z?
no. It's correct. Give me another 30 seconds and then you'll see. I'm telling you the truth. I try to always tell the truth, but I fail a lot. So do ask. But this is really correct. So a polynomial has some degree. Let's call it little p. And this is called the depth of the quasi-modular form. So let me start with the case when p is 0. So a polynomial, if p is 0, a polynomial of degree 0 is constant. So a polynomial of degree 0 is equal to its value at 0. It's also equal to the value of 17, but I want the value at 0. But now think of the identity element. This was for all C, and Z does not depend on gamma, it depends on Z. So PC of 0, substitute the identity in this formula. Then you see PC of 0, the identity, this is gone, it's F of Z. And so indeed, although there was no visible F, it's amazing, yeah. When Werner showed me that, first I said, like everyone, that, where's the F? But it's there. And another example, if P is 1, the simplest example is E2. I didn't tell you E2 before because I showed you modular forms, but I showed you Eisenstein series. And I told you that Eisenstein series, as well as E4 and E6, with these coefficients, 240 and minus 504, you can take any even number k, like E8 will have 408 and n to the 7th, and that's a modular form, and in fact, it's E4 squared. But you can also do E2. And now, for some reason connected with absolute convergence, this series converges, but some other series doesn't converge absolutely. This function, which should morally be a modular form of weight 2, is not, and instead, E2 satisfies, so I just defined it, if you take E2 of AZ plus B over CZ plus D and divide by CZ plus D squared, if it were a modular form of weight 2, this would be E2 of Z, and it is E2 of Z, except there's a small correction term, an anomaly, modular anomaly, not holomorphic anomaly here, and this term is C over CZ plus D. And you see that this is indeed a polynomial independent of gamma, but depending on Z, it's a polynomial in C over CZ plus D. So this is an example of P equals 1. And in fact, in the case of SL2Z, I already told you that this is just polynomials in E4 and E6. And then it's contained in M star. I mean, this definition works for any group, even non-co-compact, so even co-compact. But in this case, E2 generates everything. And many people just take this as the definition, but it's a really terrible definition because it's only for one particular group.
Sorry, this E2 can be converted to modular form by some.
Yes, I don't want to say that now. I won't give my own lecture, but yes, it's certainly true. No, it may come later. In the original, I said that when Kaneko and I defined, we had something else called almost holomorphic modular forms. And there's a bijection. And then you take that, that's a polynomial in 1 over imaginary part of Z, and its constant term will be one of these. But that's an indirect definition, and Van den Naam found this intrinsic definition, and I want to work today with holomorphic functions because I want differential equations. But it's absolutely true. So any F in M tilde has a completion F hat, which is in M, I call it hat, which is a non-holomorphic modular form. And in fact, it's very simple. You take this polynomial and replace C over CZ plus D by some constant like 1 over 2 pi I over the imaginary part of Y. And then that polynomial is Z. So there is indeed something, but I was hoping to avoid it, but I should have known that people would ask, because of course that's the natural question. So I'm not. Okay, so now I want to prove the theorem. So the theorem I already told you. So every modular form, and in fact every quasi-modular form, so one that make in general, satisfies, I already wrote it, but now I'm writing it as a theorem, a third order nonlinear differential equation. Well, let me say I didn't finish saying about this structure. M star tilde of gamma always is a ring. Its transcendence degree is always 3. Before it was 2. But you see in the case of gamma 1, we had E4 and D6. Now we have E2, E4, and D6. There are 3 generators. And also, it's closed under D, which is differentiated by Z, but as I already told you, I want to divide by 2 pi I. So that's what I called prime before. And since it's so important, let me take 30 seconds to tell you the rest of the structure. You also have W, which is the weight. Remember, each modular form, even each quasi-modular form, had a weight K. So multiplying F by its weight, that's like the Hamiltonian. And there's also an operation delta, which in the case that people know of d by dc is just differentiated with respect to E2. But in general, there is no E2, but there is a definition. And these things form an SL2 action. So the commutator of W and D is 2D, the commutator of W and delta is minus 2 delta, commutator of D and delta is W. So it's SL2, and the modular forms are just the primitive elements. And so this is basic in the whole structure, but I didn't want to say it at all. So now the proof is shorter than the statement. Well, especially if I add the letter F. So F is in the modular forms, the quasi-modular forms on some group gamma. But it's closed under differentiation. So is F prime, and so is F double prime, and so is F triple prime. Of course, also all the higher derivatives, but I don't care. And so that's the proof. Because this thing is transcendence degree 3. Here I have 4 elements, so there's a polynomial relation between them. So that's, really trivial proof. So the example, the dominating example, is very easy. If I take E2, which is the first quasi-modular form, also it's the lowest weight quasi-modular form at all, because there aren't any modular forms in weight 2, so it's the simplest example. And then you get Chazy's equation, which I can never remember the coefficients, but you have F triple prime minus F double prime plus 3 halves F prime squared equals 0, and this is called the Chazy equation. And the Chazy equation was known since, I think, the mid-19th century in connection, I'm not sure how early Chazy was, but later, in the, I guess, early 20th century, I've never looked at the papers, I don't know the dates, was the famous Painlevé work and the Painlevé equations 1 through 6. And Painlevé studied the question, which we'll come to later, of isomonodromy. I have a linear differential equation or a system. It has a monodromy group, but let's say that the coefficients of the differential system depend in some way on some parameter t. Then the monodromy is a function of t. But maybe a miracle happens as you vary t, it's constant. It's always the same group in some suitable basis. That's called isomonodromy, and it turns out that the condition on the coefficients is that they satisfy some system of differential equations relating, but in general nonlinear. So the nonlinear equations occur as the isomonodromy condition, and later WDVV equation of linear systems, and Chazy does that, and I'll come later to how you see Chazy from that point of view. But I want to say something fun about Chazy. If you've read the 1, 2, 3 of modular forms, which you all should every day, but you maybe haven't recently, so this is written there, so if you've read it, I'm repeating, but this is something I found by kind of chance, and it's so surprising that I want to tell you. So I define a group action if F is some holomorphic function, say in the upper half plane originally. And now this doesn't have to be in a discrete group, it's in SL2R, and very shortly it'll even be in SL2C. So I define a right action. This is the function defined by CZ plus D to the minus 2, F of AZ plus B. And now again, people will complain, certainly Samson will complain, and he'll be right, but in fact he'll be wrong because it's true. It looks impossible that what I write is correct. So this is the action. And you notice it's exactly the same as what's written here. So this is exactly E2 double slash ABCD. So you didn't complain, maybe because I warned, where's the F? You might have asked, as you did before, what's the F? This isn't even linear. This is a nonlinear action. But amazingly, it's an action. If you do F double slash gamma 1, gamma 2, it works. I mean, you just check it. It takes 4 lines, but you don't understand why it works, except it has to work. Because since E2 is invariant under this action for ABCD, if it weren't a group action, you'd get a contradiction. So it must work at least for SL2Z, but that's Zariski dense. So you don't actually have to do a calculation. But now, more remarkably, let's call this operator, which is completely nonlinear, let me call this Chazy of F. Okay? Then I now do some ABCD, but now it should be, no, it's anything in SL2R, in fact, even in SL2C. You might say if F is in the upper half plane, this doesn't make sense, but it does make sense if this is in the upper half plane. So you keep moving it around. It's like a sheaf. You have, for each gamma, even in SL2Z, you have a holomorphic function in gamma inverse of the upper half plane. You kind of glue them together. But now this is a nonlinear action. This is nonlinear. But remarkably enough, the whole thing is simply the usual linear action. Now in weight 8, on this, although Chazy is a totally nonlinear operator, and although this action is nonlinear, the answer is this. And now, as a corollary, if I take Chazy of E2 double slash ABCD, which is now even in SL2Z, then since Chazy of E2 is 0, and this is linear, so this is also 0, so this is 0. And so you get that the solution space of Chazy of something, F equals 0, it should be 3-dimensional because it's third order. It must be 3-dimensional. It's simply parameterized by SL2C, but because this is a group action, it's the orbit of E2, and E2 is fixed by SL2Z. So you get a rather nice modular space, SL2C divided by SL2Z, parameterized the solution. So this I noticed several years ago. I put it in the 123, which is a textbook. I don't know if other people had seen it, but it's very cute. I thought I would make some publicity. So now I've finished number 2. Now the third is this one will be linear again, so that's good. I won't say anything about the order. And now it is with respect to Z itself, the original variable. So that's also good. But of course, so it's these equations of type 2, by the way, are always Picard-Fuchs. I think I will take off my jacket since I'm beginning to burn. These are always Picard-Fuchs. In other words, they're the equations of the periods of a family of varieties. This one is not a period function, so the coefficients are not going to be polynomials or algebraic functions of t as they were in case 1. The coefficients themselves are quasi-modular forms. Well, then you might say that's stupid, because if I define modular forms in terms of modular forms, I've done nothing, but very special, so not at all arbitrary. So in the third class, which turns out to have many applications, time is flying. So let me give some examples. Maybe I'll put them here since it's the least important for my lecture. Eventually I'll have to do some erasing. So here's an example. I'll call it star. This is called the Kaneko-Zagier equation. The same Kaneko I mentioned is sitting there, but not in the same paper. Maybe it is. No, that's not, I think not in the same paper. So let the equation be the following one, f double prime minus k plus 1 over 6. K is going to be the weight. E2 times f prime plus k times k plus 1 over 12. Again, the details in here, I put E2 prime times f is 0. And what we found is that if k is an integer, which is congruent to 0 or 4 modulo 6, and I define fk of z to be E4 to the k over 4 times the hypergeometric series minus k over 12, 4 minus k over 12, 5 minus k over 6, and again 1728 over j, just as before, then that implies this equation. And the reason we were doing this, we were studying supersingular primes, and if k is p minus 1, and that's why I didn't want k to be 2 mod 6, because then k plus 1 would be divisible by 3. If with p prime, then fk in a suitable sense, modulo p, is the supersingular equation in characteristic p. So if you look at elliptic curves over fp, which are supersingular, that means that the set of points over fp bar has no p torsion. They're very rare. They're only roughly a finite number, roughly p over 12 of them, and the roots of that are exactly, after you change this into a polynomial in J, they're exactly the roots of this polynomial. That's not important for my lecture, but it's an example. But although this equation is called Kaneko-Zagier, our paper was, I think, 1995, it actually had occurred earlier, but we didn't know in the context, so I'll call these, so the good equations, so I said they're not arbitrary, they're called modular linear differential equations. So there's a condition that I won't say. I just finished a paper. It came out on the archive, and it's already in the journal, with 2 other Japanese colleagues who are not here, Kiyokazu Nagatomo and Yuichi Sakai. So it's about a year ago. We classify all MLDEs. Actually, we give about 5 different ways to classify them all, but it all comes down that there's an isomorphism, but several canonical isomorphisms, between the set of modular linear differential operators. That means operators that have the property that they're potentially, they have modular solutions, so they're compatible with the modular group. I don't want to go into detail. This is an example, but these operators have become very important in the last 15 or 20 years in the theory in conformal field theory and the theory of vertex operator algebras. And the reason is, if you have a nice vertex operator algebra, maybe simple, and you look at it itself or any module, say the irreducible modulus over it, these are graded vector spaces. So there's a power series, the sum, the character, the sum, the dimension of the kth piece times some variable to the k, and they always satisfy such, well, not always, but in a large class of case, they satisfy modular linear differential equations. So in particular, a very beautiful case is if you take what's called the 2-5 minimal model, many of you know much better than I do, then it's a second order equation, and the 2 solutions are the 2, I won't write them down, I think everyone has seen them, the famous Rhodes-Ramanujan functions, which are either the left-hand side or the right-hand side of the famous Rhodes-Ramanujan identities. Those 2 functions are the solutions of exactly this parameter, but now k is, I think, 1/5. So they satisfy the same equation star with k equals, I think it's a 5th. I'm not sure if I could work it out. But.
Is space of solutions, like in Chazy case, is some kind of orbit here? Or?
Wait, no. These are linear differential equations. The space, this is linear. The space solution is a vector space for dimension 2, and the base is Rhodes-Ramanujan. Now we're back in linear.
What is the minimal model?
I don't want to talk about it. Many people here know. It has nothing to do with my talk. For those people who know, this is one of the simplest, and there are many others. I'll maybe mention one other example. So Rhodes-Ramanujan, I assume everyone knows, because if you don't, then tonight look it up in Wikipedia, learn it by heart. Many people say they're the 2 most beautiful identities in mathematics. So these are famous functions. They're called G0 and G1, and these are the independent solutions of this when k is a 5th. But the applications of this are if you have a potential vertex operator algebra. So for instance, a paper of a few years ago by Fricke and Nagatomo.
So does K have to do with the Rasora central?
No, I don't want to talk about physics. So I don't want to say anything. I want to go on with the lecture. Questions you can ask. This part is not part of the lecture. It's just a remark that these have become important in recent years because I do not want to go into this at all. But I'll just say that there was a certain vertex operator algebra that looked like it might exist with central charge 164 over 5. Nobody knew if it existed. They wrote down the corresponding modular linear differential equation. It's 3rd order. The 3 solutions, this is unbelievable, so listen carefully. The 3 solutions they write down, it takes 2 pages, are homogeneous polynomials in G with 0 and G1 of degree 82, with coefficients, gigantic coefficients, they cross the whole page. So you have three immense polynomials, and those are the solutions, but some of their coefficients are negative, so they can't count anything, and that proves that there is no vertex operator algebra. So this theory of modular linear differential equations, it can also be used positively. Some equations were constructed because you solve the equation and you show it does exist. So I just want to mention it because there are many physicists, including Maxime, although he says not quite. Okay, so let me go on.
Don't, but for mathematicians, beyond the discrete series of minimal models, are there...
Well, there's no minimal model in this talk. I cross that out. The talk's about modular forms. I cross this out. Any questions about that, please, afterwards. I would like to finish my talk. I do not want to talk about minimal models, please. I don't know. Please, I would like to tell the interesting part related to Maxime's work. And the time is flying, as it always does. Exactly, I always try to speak faster, but then other people are unhappy. So I will try not to speak faster and to make everyone happy. So the fourth sort came, and this was inspired from something I've been thinking now for almost 30 years. Boris Dubrovin spent a year in Bonn, I think 1997, roughly 1997, working with Yuri Manin on Frobenius manifolds and so. And we didn't yet become friends. He seemed much older. He was 1 year older, but he knew so much. But he explained to me about Frobenius manifolds and about Maxime's equation. And later we became colleagues in Italy and we became friends, wrote several papers together. But he explained something, I'll come back to that. This has to do with counting rational curves through a fixed number of points in P2, so quantum cohomology of P2, or Gromov-Witten invariance in genus 0 of P2. But there are simpler examples, all coming from Frobenius manifolds. And what I only found recently through joint work with D. Young, and some what I'll say is with a student of his called Zhengfei, well, I guess one should put the names, but the collaborators to Young, and many calculations are being done. If we ever succeed, it'll be a joint paper, but for the moment we only have lots of calculations. But in this theory, you get nonlinear differential equations automatically. And the way you get them is what I already said, but not explaining about Chazy. You have a linear differential equation, depending on the parameter, and the condition on this parameter that it have isomonodromy is some sort of a nonlinear differential equation, sometimes an associator equation. So I'll try to come to that at the end, but first I want to give a somewhat simpler example connected directly with the Chazy example. So now I don't know where I carefully made 3 pages of notes that I wouldn't lose and put them on top, and of course now they've gotten permuted. Well, I have an approximate version. So the third is, again, nonlinear differential equation. I'm not going to keep putting the bad and good, but now with respect to something else. So it's not even with respect to z, so it's bad, it's doubly bad. However, so that's bad, but it's now second order in general, but no longer autonomous. So it's a polynomial typically in f, f prime, and f double prime, and z, the dependent variable. Okay, so let me try to give the actual example. Oh no, it is more or less here. So let me give this example. I think now there's no way around. Oh, there is a way around it. I thought I now have to erase, but I have a whole other board. So the last example is I take, as I said, you start with the linear differential equation or system. So gamma will be a function of a parameter z, and when I write gamma prime, I mean the derivative in z. Here I have this, the next coefficient, the details don't matter, but for completeness, I'm writing them all down. So let me look at this linear equation. So W is a function of x, and the coefficients are like this. There are several coefficients, but they're related. Gamma is a function of z, and then this is gamma of z plus gamma, and with gamma prime of z, and so on. And then you find that the isomonodromy of this the isodromic equation of this is Chazy. And in fact, to be very precise, it's rescaled, so I think it was 1/6. Yeah. So if you take gamma of z to be 1/6 E2 of z, this modular form, then this thing has constant monodromy. And in fact, you can solve it. So this equation comes from a Frobenius manifold, which, and if anybody asks me questions, I'll have to refer to somebody who knows, because these are just words to me. This is the A11 Frobenius manifold. I mean, I know more or less what A11 is. I know the potential of this. I don't want to go into it. There is a Frobenius manifold which leads to a solution, a certain equation. It's not this equation. This equation you get by applying the so-called Legendre transformation to the basic one, and then you get something nicer. And the same will be true for Maxim's equation, at least we hope. So this is.
So which dimension Frobenius?
Oh, sorry, three-dimensional. All of my manifolds are three-dimensional. Let me remind you in one word what a Frobenius manifold is. It's something complicated, but if it's three-dimensional, if it's n-dimensional, we'll put n variables here. It's a function of 3 or n variables, which has the property, there's an associated function called the potential, and roughly, well, not even roughly, if I define a multiplication on tangent vectors, or these cotangent vectors I can never remember, if I take the sum over, maybe I'll call it alpha, beta, gamma. If I were a physicist, I would drop this by the Einstein summation convention. I take the third derivatives of x, and then here I take d by d x gamma star, which is some isomorphic. In our case, it's just 2 minus gamma. So again, it doesn't matter, but this is an equation, and this should be associative. That's the famous associativity equation, or WDV equation, associative. But whatever it is, it exists. Here you can write down the potential, have it written down, but it doesn't matter. And this is the differential equation, and the associated nonlinear equation for isomonodromy is Chazy, and it's E2. But now, as we've heard in a couple of talks, like in Misha's, when you have such a thing in quantum cohomology, that's the A side. But on the B side, these are the periods. These are things that satisfy typically a linear equation of Picard-Fuchs types. That's this kind. And you get it by a Laplace transform. So here there are several very pretty formulas, but I'm not going to write them down because I'm running out of time. If you write down the solution of this, of course there are 3 solutions. So the solutions, it turns out, will be polynomials, power series in X. There are 3 of them, and I could give you the first few terms, whose coefficients are quasi-modular forms. But then by small change of variables, you get some other variables, Gj, j is 0, 1, or 2, which are also power series in X. But now you've eliminated the E2 part, so these are simply polynomials in E4 and E6. So they're very nice. And now you take Gj tilde, which is the Laplace transform. So if the original one was x to the k, then you replace it by, I think, k double factorial, which is the product k minus 2 down to wherever it goes, divided by x to the k plus 1. So you get a new function, Gj tilde of capital X. So this is now on the period side. And then these, you can satisfy, that's very pretty. This I did 2 or 3 years ago with De Young. You can satisfy, give them in closed form. You write down the elliptic curve. So the nicest way to write down the elliptic curve associated with Z in the upper half plane with no 2 pi's and so on is like this. So X is this new variable, capital X. Capital Y is this variable. So you can think by Weierstrass, X up to a constant is some P of U and Y is P prime of U. And now the solution space is X, which is the X coordinate P, divided by Y, which is the Y coordinate, which is P prime. And then the three solutions are 1, u, and zeta of u, where zeta of u is the Weierstrass zeta function, whose derivative is p. So it's a completely explicit solution, in this case, of the period solution, but not of the original equation, of the original system, but afterwards called the Legendre type transformation. So now I want to end with the example that I'm so, that I so love, but it has never worked. I've been trying now for 30 years since Boris Dubrovin told me this story, and I fell in love with the equation. And I had a dream then, but all of my friends told me that the dream couldn't be true. So people like Sascha Benitz and others, they said for reasons of Hot theory, the naive version of the dream, which is what I first had to be false. So I gave up. But then 2 or 3 years ago, we realized that you don't have to be just the naive way. And now I'm actually very confident that there will be a modular solution. So I want to end very briefly by telling you, for most of you recalling, because many of you know it, and some of you know it much better than I do, I want to recall very briefly what Maxime did and what I did when Dubrovin showed me this story and what we think we can do now. So nk is the number of rational curves in P2 of degree k through, well, the right number to make it a finite number is 3k minus 1 generic points. So it begins, n1 is 1 because there's one line through 2 points, n2 is 1 because there's one quadric through 5 points, n3 is 12, n4 is 620, and so on. And these numbers were of great interest, but people didn't know how to do it. And what Maxime showed is that if you take the corresponding generating function, the sum nk, it's convenient to put a 3k, and you certainly want to divide by 3k minus 1 factorial, then this satisfies a nonlinear equation. Just for completeness, I'll write it out, but it plays no role at all. It's quadratic, so it's not linear. The linear term, it's third order. So the linear part is this, and the quadratic part okay, it doesn't matter at all. That's the equation. And so the dream that I had is, now if you write down this thing and just write it out, this gives a recursion for nk. And with the recursion, it shows that the nks are explicit integers. They grow very quickly. You can give the growth very precisely. It was done by Differential and Itzigson, and we can make it even more precise. So this tells, in a sense, this solves the problem. And most people say, Maxime solved the problem because here's an answer. But we don't usually say that it's a solution to give a differential equation. We usually want to solve the differential equation. So the question is, so a question that I've been dreaming for 25 years, can one give an explicit formula? You don't expect an explicit formula for the k coefficient, but an explicit formula for h. And so explicit could mean many things. So let me say that in this case of Chazy that I just wrote, I told that the original equation was a different one, this the Laplace transform. This transforms into a new nonlinear equation, which is not Chazy. And that one, although it's third order, it's actually second order non-autonomous. It's the derivative. So it's even better. That's what I was saying, this fourth class. And so I didn't put it yet. I meant to add that to Chazy. In the Chazy story that I just gave you, it leads to a different. I told you there are these things called Legendre transformations. It's a group of order 3. So if you apply one of them, you get a different nonlinear differential equation, not the Chazy equation. And I have it written down, so maybe I'll even tell you that now my pages are no longer in their original.
So linear equation is not known for which this is a...
Wait, I'm talking here, it's completely known. I was going to write it down, but I can't find it in my notes. Here it is. The nonlinear equation here. So the original nonlinear equation for the Chazy case was the Chazy equation. That's the one I gave. This was the system. Then you apply this Legendre transformation, you get a different one. And that one is f double prime minus f prime times 3f prime minus 5f. You notice no third derivatives. but it's minus 48 x cubed. So it's not autonomous, there's an x. Of course, if I differentiate this and eliminate x, I'll get a third order autonomous equation, but this is better. Okay, and now the solution of this is the very remarkable thing. The solution, but now I don't have the coefficients in front of me, so I might get it slightly wrong, but I did. I'm sure I wrote it down because it's so, here it is, yeah. So it's not 1/12, it's, if you now substitute not z or t of z, but instead 1/24 times e2 prime, which is a quasi-modular form of weight 4, then this is 1/2160 times 5 e2 cubed minus 6 e2 e4 plus e6. So here you have a different kind, that's my fourth kind. Now you write your unknown function, the solution of a nonlinear differential equation. The variable is not z, it's not t of z, it's itself a quasi-modular form. The right-hand side is a quasi-modular form. And that's now a much bigger class. That's my fourth class. And my hope, of course, and I was hoping I'd be able to tell you the answer and end with that, was that Maxim's equation after this Legendre transformation would lead to that. But let me stay, nevertheless, a few more words here. So here there's an explicit system, explicit linear system, which I have in my notes, but I won't write down. So it's a LDE, so it's a system of 3 first-order equations or 1/3 order equation. And it gives this equation as the isomonodromy or Witten-Degraaff-Velinde formula. So the condition, so that's the part that Maxim did. But then Dubrovin asked me, he knew that the monodromy of this linear system was some group of SL2Z. He wasn't sure if it had finite index, and I'm a modular person, he asked me. So I said the following: if it's isomonodromy, the monodromy group is independent of T, let's take T equal to 0, so before you deform. Then I looked at that system. It's very easy to solve it in terms of hypergeometric functions. So now the LDE, the linear differential equation, has a hypergeometric solution. I won't write it down, but it's very easy. But then what I found is it becomes modular after a change, just like in these examples I gave at the beginning. Like here, you have a hypergeometric equation like, oh, sorry, I made a terrible mistake. I don't want to get it. F of z, somebody should have stopped me, Samson, you fell asleep. The order of the differential equations, k plus 1. E4 has weight 4. F has weight, second order differential equation, it should be f to the 4th, excuse me. F to the 4th satisfies the 5th order equation. So that's a typical thing. You have an explicit hypermodular thing, but after you make some clever change of variables, and I found it, so you had to take essentially the cube root of j of z was the transformation as the independent variable. Then it became quasi-modular. So I could give a completely modular and quasi-modular solution of the equation at t equals 0. In particular, that fixed the monodromy group. It was the unique normal subgroup of SL2Z of index 3. But that means that's always the monodromy because it's isomonodromy. So then I said, surely, if it's always SL2Z or this silly subgroup, there must be a modular parameterization of the full thing. And then, as I said, people like Sascha Benenson, Martin Müller, several people said, no, for reasons of Hodge theory, you cannot have a straight substitution like the one I did here, this one, of a modular function and get this differential equation. It's impossible. But in fact, we have an extra variable because it's exactly a 3-dimensional manifold. And so it turns out you can introduce a second variable, and then you suddenly have 2 variables, z and z prime, with the group gamma acting simultaneously, az plus b over cz plus d, and az prime plus b over cz prime plus d. And this is something that I introduced and studied many years ago, originally alone in a very short note that I never published, on a question Waffe asked me on the holomorphic anomaly equation. And then I worked for several years with Jan Steenstra, and we elaborated a very beautiful theory, but we never finished writing the paper. I should contact, we really should. It's mostly written. And we have a theory of bimodular forms. These are functions of 2 variables in the upper half plane, which transform in some nice way when gamma acts simultaneously on both of them. And in this, using a transformation that actually was found many years ago by Dubrovin, but I only learned about it a week ago, there is a transformation of a complicated thing also using the Laplace transform, going back and forth, but you end up with new variables, z and z prime, which are in the upper half plane, with gamma acting diagonally on this. And because of that, I'm now very sure that there will be a way to write these. We have all of the expansions of all of these functions. So the original one at t equals 0, I gave a modular description. After you vary, then you get power series in t whose constant terms this modular forms. The higher terms are all quasi-modular. We have calculated many of them, and we're trying to recognize those series in closed form. And I'm basically quite confident that it will happen. And the point of this lecture was to tell you the solution. But since I don't yet have the solution, there was no point, so I stop. Now, yeah, your moment has come.
The discrete set of examples of VOA for which is properly satisfied.
Well, I'm just a finite person, so I only know finitely many examples. I have no idea. Actually, I'm not quite sure what you're... So any nice VOAs, all rational minimal models and many, many others, lead to modular forms and have characters, and they always satisfy modular linear differential equations. So it's at least countable. Whether it's discrete, I've absolutely no idea. There are many people to ask, but I'm not one of them. I've never worked actually with or...
Not too many.
Well, then you have to ask other people, but it remains that whatever the group is, I'm not a member of it. But it was just a general comment that this type of equation, which is now completely classified. My recent paper you can find on my website or in the archive with Nagatomo and Sakai, and we give many, many references to the literature because they both come from VOAs. That's why they got interested. In that paper, first we tell the story completely from the beginning. Many examples, including the Kaneko-Zagier example with supersingular, including the minimal model, including several others. And then the general classification that the equation, as I said, you cannot write, if you change this 12 to 13, this equation is no longer a modular linear differential equation. There's a very subtle condition that was basically worked out by Sakai, but it was complicated and we found simplifications, much more general. There's an isomorphism, as I said, between the collection of all such modular linear differential operators and all quasi-modular forms. That, of course, it's a vector space over C, so it's got discrete parameters. But which of those, so the collection of modular linear differential operators has, well, it's exactly m star tilde of gamma 1, which I told you is just polynomials in E2, E4, and E6 with complex coefficients. So that has continuous parameters. But which of those actually come from vertex operator algebras, I have no idea. I only know that that's why people care, because, so in one direction it's true. Nice vertex operator algebras, so for instance, rational minimal models, but many others, do lead to modular linear differential operators, and those are the ones that you use to understand the solutions and the modules better. But I don't know if they all do it. My guess is that is discrete. Ours, the set of operators is continuous. But
is the significance of the zeta 3 being irrational represented in this modular expression?
No, first of all, as far as I know, there's no significance in zeta 3 being irrational. The only reason that Apéry became so famous is because the problem had been open since Euler. Euler wrote his famous paper, well, two papers, but the first one in 1734, where he proved zeta of 2 is pi squared over 6, zeta of 4. And he said, zeta of 3, I've tried very hard. He calculated to 20 digits because he had found a very accurate way to calculate. He said, I can't recognize it. And my guess is you cannot write it in terms of known functions. That's still true today. And of course, people wanted to know if it's irrational, but even if you're a good number theorist, you know that's the wrong question. The question is zeta of 3 divided by pi cubed rational? Because it's the wrong weight. So of course, it shouldn't be rational, but it also shouldn't be, but the thing it might be, I mean, more plausible is a rational multiple of pi cubed, we still don't know. As far as the significance, there's none. Zeta 5 is also irrational to 10,000 digits. We're sure it's irrational. And there are similar formulas, but they aren't in closed form. They don't give enough convergence. I wrote a paper that I've mentioned to you when we talked yesterday called Apéry-like differential equations, which was a class of differential equations that included Apéry's proof for zeta of 2. Zeta of 2 wasn't so famous because it was known, but he gave a similar proof and Berkus gave a similar modular interpretation. But it turns out that it's very, very rare that you can do that. But there were still 6. And the corresponding constants, 2 of them were zeta of 3, but 1 of them did not converge well enough to give irrationality. 2 of them were the famous Catalan constant, which is, in the notation of number theorists, L of 2, but for the character chi minus 5. That's still not known to be rational. And the last one I had was L of 2 chi minus 3, which is also a famous number. And again, it gave a formula that converged, but it converged too slowly to give irrationality. But about 1 month ago, 3 authors, the only one I remember is my friend Frank Caligari, sent me the paper. I've now forgotten the names of the 2 authors. This was solved just a month ago, huge 250-page paper using the modular parameterization, but some very clever change of variables that made it converge better. As I say, a 200-page paper, it's not easy. But it's completely random which numbers you get. So some of the others you can get approximations, but they don't converge quickly enough to give irrationality. So it's kind of just an accident. There's no real significance to it.
One last question.
One more, then David.
The LDE, there, is it related to open string?
How would I know? I don't know what an open string is. I can ask you, is this LDE related? No, I use words. I use words, I don't know what they mean.
All right, let's thank